Welcome back to another episode of Data Skeptic Animal Intelligence. Today we've got a somewhat technical one exploring the role of hidden Markov models and the types of research we're covering in this season. Becky, for background, were you familiar with hidden Markov models before this interview?
I was. It was from a bioinformatics perspective. And then when I took bioinformatics, I realized one of my lab mates did it with bee behavior as well. So I know what they are. I've plugged stuff into them, I suppose. With bioinformatics, you're really just hitting a button. So no one should be impressed by that. But so I am familiar with them.
Yeah, they're a well-known topic in the data science world too, though also a technique very few people get to utilize, at least from my casual survey of people. Which kind of makes sense, and also why you would need them in this context. Animal behavior is not a stationary thing. You know, animals have different states, from simple things like sleepfulness and awakefulness to sort of angry, agitated, happy, and all these other kind of emotional states. So having a system that can perhaps infer that those exist and to do something about behavior related to those inferences is a powerful tool.
Absolutely. I think in behavior, hidden Markov models are wildly underutilized. I think they're getting more and more popular. But even if you're not interested in the animal's internal state, let's say I want to know if some ground squirrel is being stressed by climate change. And I have squirrels in hot area A and cool area B. And I have enough environmental data about like wind speed and ground temperature and humidity. Can I predict their behavioral states? Are they sleeping? Are they foraging? From abiotic data. So to me, that's also super fascinating, is could we actually look into some natural history and ecology with hidden Markov models?
Very cool idea. Yeah, I like them as well because they're very much on the path towards your typical agent architecture. There's something I studied called a partially observable Markov decision process, or POMDP, which is sort of like a hidden Markov model with some extra features. It's able to account for like utility, what the goals of the agent are, and what actions they have, whereas HMMs just cover the state, but they cover it in a probabilistic way, which is, I think, key to a lot of good agent frameworks.
Okay, that might be really interesting for some pollinator research that I've seen, because we know the goal already, what the bee's up to.
Right. Yeah, that's a novel idea.
I did have a question for you about hidden Markov models and behavior, if you're up for it.
For sure.
I've been thinking about this, and it makes sense to me if you have a supervised model where you've done some experiments in the lab or previous field observations, and you know the different states that your animal is going to be in and what factors might determine those states. But if you have an unsupervised model and you're just comparing animals from category A and category B, well, what kind of information can you get from that using an HMM?
So unsupervised is a big category. Like clustering algorithms, the goal is get some clusters. Now, how are those useful is up for grabs. In an HMM, it's a different sort of unsupervised thing. Like in supervised learning, you can have logistic regression and XGBoost and a bunch of things that are very different under the hood, but all after the same task. So unsupervised is a lot more heterogeneous in this regard. So an HMM specifically, it kind of infers or maybe helps you debate what the actual internal state is. So if you take a real toy textbook example, it's like a robotic vacuum cleaner, maybe that cleans two different rooms. So there are four states, two clean rooms, one or the other is dirty, and both are dirty. Now that's, a simple kind of toy example. In the real world, you might not know how many states. So maybe you test out a variety of HMMs to say which is most consistent with our observations, and then have some sort of Bayesian distribution over the one that is most applicable to your observed data. I guess there isn't explicitly a goal. It's just calculate the probability that this model explains this data. And then based on a Bayesian approach, you could kind of inference something that you're concerned about, that you care about, that maybe the most likely number of internal states is 6 or whatever that is. And then something, if you have a good model, about inferencing from that. So what would it do under other conditions you didn't observe?
Okay, I think that makes sense. And the example I'm relating it to in my head is animals in, and this is a study a friend of mine did, in suburban and urban and exurban areas, and she was looking at the pattern of behaviors to forage, and they were different in each category, and she used an HMM to look at the order of those behaviors. So those would be the states.
Yeah, so there's a sequence that's interesting in that case. And that's a great place for an HMM. Very few methodologies can process sequential planning and sequential data and stuff like that in that regard. So if she's able to observe these patterns of behavior, maybe there's some loops within the behavior tree, an HMM is very descriptive of that situation. Well, could you introduce some of the content of the interview today?
So Theo he's really interested in time series data, so movement of animals. He had a really interesting paper that seemed to be less about time series, more about decision making in some ants in a laboratory colony. But knowing what an animal is up to or how their behaviors are different if they have a GPS collar on is really fascinating, because it's pretty rare we film them all the time. We just know their locations. So to figure out exactly what's different with these massive data sets at this point is really challenging. To have someone who's really into something like HMMs, or even when you hear from Theo, you'll hear there's lots of other techniques as well. It's really helpful to ecologists.
Is this something that's come about because we have the computational power available now, or has it just been adoption that's taken time?
I think it's a bit of both. For me, I would still have to access my university's HPC, or high-powered computing cluster. I wouldn't just have a computer in my lab that could handle these data. So I do think it is a computational issue, but I also think it's a adoption issue. One thing you and I have noticed with a lot of our guests is on these multi-author papers, there's usually the machine learning AI person, and then there's the ecology person that went and put the collars on the animals. And these seem to be a little bit discrete. So unless you know one of those people and you know enough about machine learning, AI, that kind of thing, to even ask the right questions of that person, you're probably not going to adopt it as a technique.
Good summary. Let's jump right into the interview. Well, the one constant in my own career is lifelong learning. I've never been able to rest on my laurels. So if you're looking to pivot or to grow and become a data-savvy leader, consider the Georgia Tech Scheller College of Business. They offer a 100% online business analytics graduate certificate program. It teaches professionals how to analyze and interpret data. The online program's got 4 courses: business analytics for managers, machine learning for business data prep and visualization, and analysis of unstructured data. That is a great coverage of topics to prep you to be a professional in any industry. This program definitely allows a work-life balance, so if you've got a lot going on, it'll fit in. If you want to push hard, you can take 2 courses a semester and graduate within a year. The Business Analytics Graduate Certificate can be your gateway to a Georgia Tech MBA. You can apply select credits towards the Georgia Tech full-time MBA, evening MBA, or online MS in Analytics. So are you ready to become a data-savvy leader? Get the skills necessary to do that. Applications for the Georgia Tech Scheller College of Business Business Analytics Graduate Certificate are open now for spring 2025. Visit techgradcertificates.com to learn more. And don't forget to apply by October 1st. That's the deadline. For more information, head over to techgradcertificates.com. In 2023, just 10 vulnerabilities accounted for over half of the incidents responded to by Arctic Wolf Incident Response. Wouldn't you like to know how to take them off the table and make life more difficult for cybercriminals? That's just one of the essential insights you'll find in the Arctic Wolf Lab's 2024 Threats Report, authored by their elite team of security researchers, data scientists, and security development engineers, and backed by the data gained from trillions of weekly observations within thousands of unique environments. This report offers expert analysis into attack types, root causes, top vulnerabilities, TTPs, and more. Discover the attack vectors behind nearly half of all successful cybercrimes, why ransom demands climbed 20% from 2023, and find out why 2024 will be an especially volatile year for cybersecurity. I got my copy. You should get yours by going to arcticwolf.com/dataskeptic. That's arcticwolf.com/dataskeptic.
Yeah, hi, I'm Théo Michelot. I'm an assistant professor in statistics at Dalhousie University in Canada. My undergraduate was in kind of applied math, but ever since my master's and my PhD especially, I've been more of an applied statistician. And basically, ever since I started working in statistics, I've been interested in ecological data analyses. So it's all been developing statistical methods and statistical software for analyzing usually time series data in ecology.
And for listeners who aren't ecologists themselves, could you share a little bit on the nature of the data? What kind of observations do you have?
Yeah. So I mean, actually, I'm fairly specialized within that broader kind of field of ecological statistics, and specifically, I work usually on tracking data. And so, tracking data is anything where you put a tracker on an animal. And I know that you've had episodes that have kind of covered other examples, but it could be, a GPS collar that you put on a wild animal to see where they go. So in this case, you would end up with a time series of longitude, latitude observations through time, or it could be something like an accelerometer. And so usually those run for kind of at a higher frequency for shorter periods of time, but you would try axial accelerometry of the animal for some period of time. And then those are really just time series data. That's how a statistician would view them, and so we need time series models to analyze them.
Well, you're obviously working in both statistics and ecology. There's an overlap here, but people might think of them as independent fields. What was your journey like into these two areas?
So I was really lucky to work as an undergraduate and then a master's student. I got to do research placements at a research center that's called the Center for Research into Ecological and Environmental Modeling at the University of St Andrews in Scotland, and it's one of the kind of really world-leading teams in statistical ecology, which is a small but quite active field of research where essentially, I mean, as you say, it really brings together ecologists and statisticians because ecologists are more and more interested in having, better data analysis methods and software and so on. And statisticians often find ecological data and ecological questions really challenging and really interesting because there's all sorts of problems that come up from the often the temporal and spatial nature of the data, complex correlations, many individual animals, interactions, and all those different things that need to be somehow accounted for in modeling. And so I think it's a really, really fun playing ground for both ecologists and statisticians. And I've really been enjoying having great collaborations. I'm a statistician myself, but I work, I think probably most of my colleagues are actually ecologists. Some of them, field biologists, and others more kind of theoretical ecologists. And it's been kind of amazing to learn from them about these data and the kind of broader ecological questions that they have.
Well, in terms of methodology, what sorts of techniques are either maybe effective or popular or both in the field?
So there's a really very broad range of methods, as you can imagine, just because there's very many different types of data and questions. So if you collect survey data on fish by from maybe fishing vessels, and you're interested in knowing how many fish are left in the ocean, you're going to be using methods that are very different from someone like me who is interested in trying to model the dynamics of animal movement from tracking data. So maybe I'm going to answer specifically for maybe animal movement modeling, which is the kind of subfield in which I am. The data that we have are these time series data. So we have time indexed locations or accelerations or things like that. And we're interested in trying to learn something ecological about the underlying process from those data. So naturally, people often use time series models, and there's tons of those as well. The kind of basic building block of a lot of those are essentially very simple stochastic processes, things like random walks that essentially try to account for a short-term correlation in the animal's movement, in the animal's position, and its behavior. And then from there, we can make things a little bit more complicated by using, random walks that maybe change through time in such a way that we can model changing behavior of an animal and things like that.
And in that random walk, is that the model of an individual or is it something more aggregate?
Usually it is just the model for one individual. And I don't know a whole lot about collective animal movement modeling. That's kind of a little bit of a separate field of study. So usually I have data from one individual, actually often from multiple individuals, but in some sense, we're interested in knowing for each individual, how do they choose essentially where to move next? We know where they are right now. We want to know where they move in the next half an hour, in the next day or something. And so we want to try to model, in some sense, they're kind of movement decisions at this fairly fine time scale.
Well, if one starts from like a pretty plain vanilla random walk approach, it's pretty easy to implement, I think, in general case. And it has just a couple of parameters to play with, which is nice. So it's not like millions of parameters to worry about. But that might be underfitting. It might not be complex enough to describe the behaviors you're interested in. Then you have to take on some complexity.
How do you manage that trade-off?
This idea of using random walks, and I think random walks come from physics, and at some point in the 50s, 60s, 70s, people started to think about how you can actually use those for animals as well. And at the time, the data were really coarse over very short periods of time. Essentially, the data were coarse enough that those very simple random walks did a good job. And then at some point, people started collecting data over longer and longer time periods. And so what happens when you do that is that you realize that a simple random walk, which, as you say, might just have a couple of parameters that control something like the speed of movement, doesn't work so well anymore because the speed of movement varies with the time of day, for example, right? An animal might be resting during the night and be active during the day. And if you only observe the animal over an hour because that's how long you're able to follow it or something, you won't realize that. But once you are able to deploy those GPS tags and so on wild animals for weeks, months, years at a time, then you really need to have more flexible models. And so the kind of general class of models that I've worked on a lot that tries to address this problem is called hidden Markov models. And the idea with hidden Markov models is that we want to somehow account for this time varying behavior, but we don't observe that directly. The only thing we observe is the animal's movement, those positions that we observe through time. And so essentially we want to somehow link the movement variables that we observe, that we somehow collect from those tags, from those GPS or accelerometer tags. We want to link those to an underlying kind of internal state of the animal. And we want to somehow be able to say when the animal is moving slowly, it's probably resting. When it's moving a little faster, it might be foraging. When it's moving even faster, it might be in transit between areas of interest. And then once we're able to make that link, we can really have a much more flexible movement model where the animal behavior, the animal's movement patterns change through time.
I think the one of your papers I read, identifying cues for self-organizing nest wall building behavior in the ant rock using hidden Markov models, is a really good example of that implementation. Could you describe that process, maybe starting with the state space of the ants so we understand what their behavior is?
Yeah, so in that example, actually, that was not quite a typical example because we weren't looking at animals that had been tagged. This was kind of lab data where ants had been filmed. So we had access to a lot of individuals, and I didn't do the data collection. This was with collaborators who are behavioral biologists. The interest there was in identifying kind of high activity and low activity periods in the colony. So this was all in kind of a lab setting, but there was a whole ant colony that was being filmed. And essentially, what the ants are doing, I wonder if maybe this was focused specifically on worker ants, is that they would collect rocks and then deposit them throughout their day. And we were interested in being able to identify periods where a lot of ants were being active, a lot of workers were depositing those stones, and periods of time where they weren't. And then trying to link that to stone density. So knowing, depending on how many resources they have available, how active the whole colony is.
And in terms of switching between states, why is that hidden? Why hasn't science maybe figured out that it's, some internal clock or the exact mechanism behind it?
Right. I mean, I would say that animals are really complex, right? They're very complex. There's so many things that affect their behavior. In some cases, we know exactly almost what their behaviors are if we have essentially rich enough data. So if we attach an accelerometer tag on an animal, and then if we have the patience of going through, those maybe, sub-second observations over long periods of time, we might be able to very specifically identify when behavioral transitions happen. It might be that you'll have a period of multiple hours with almost no acceleration where you as a biologist, an expert in the behavior of that particular species, are very confident that that corresponds to resting behavior. And then all of a sudden at, let's say at 8 past 7 a.m., all of a sudden the acceleration increases and you know that the animal just woke up. And that's, an example of a behavioral transition that is almost directly observed. Most of the time, we don't have access either to the data or we have the data, but we don't have the ability to actually go through the data in enough detail to be able to identify those. And so that's what we want these models to do, either kind of in an unsupervised way or where we just tell the model, try to divide the identified clusters in the data that correspond to different types of movement, and then we will post hoc try to interpret those as behaviors, or in a kind of semi-supervised way where we have a pretty good idea for what the behaviors that we want to identify are. And then we give this information in one way or another to the model, and the model might be able to kind of automate the process of identifying phases in the time series data where each behavior is occurring.
I know it's not a direct analogy to like a kind of traditional machine learning classification problem, but does it start from a data set that you train on, or is there something slightly different going on?
So the most common way that I use these models is actually as a clustering method, if anything. And one way we can think about hidden Markov models is as an extension of a mixture model. So if you think about a mixture model where you think that the data that you have, the observations that you have, don't just come from one distribution, but from some mixture of distributions, essentially a hidden Markov model starts from the same place where we say, whatever movement variable I'm observing doesn't just come from one distribution, it comes from multiple different probability distributions. And which distribution it comes from depends on what the animal is doing. And so the extra layer of complexity that a hidden Markov model has over a simple mixture model is that it has temporal dependence in what mixture component is active at each time step. And so we often also call them dependent mixture models. If I know that the animal was resting 5 minutes ago, it's very likely that it's still resting right now. In terms of the model, it means that if the first mixture component was active 5 minutes ago, it's likely that it's still active right now. And so essentially, we think about those multiple distributions, and we are interested in knowing how we transition between those distributions.
While the technique sounds sound and it all makes sense to me, it's not just a plug and play activity. Could you talk about the process of going from raw data into formalizing it and building up that model?
There is some data preparation required because the variables that we typically input into these models aren't actually raw variables that the tags provide. So the tags give us things like longitude, latitude for GPS tags, for example. But longitude, latitude itself doesn't give you that much information about essentially the movement patterns of the animal. And so usually the first step is to get variables like step lengths. So those are distances between successive locations, or turning angles, which are angles between successive segments in the trajectory. And those are much more informative about what the animal is doing because step length tells you something about the speed of movement. So long steps correspond to faster movement, while short steps, slower movement. And turning angles tell you something about how tortuous or how directed the movement is. So if the turning angles are very close to zero, then it means that the animal is kind of moving in a straight line. Biologists can often identify behavioral states based on those variables because if an animal is moving fast and directed, it's probably transiting. If it's moving slow and undirected, it's probably foraging or resting or something like this. So the first step is to derive those variables of interest. It becomes even more interesting and potentially complex when we look at richer data. So if we had accelerometer data, for example, there's a lot of different things that we could do with it. Often, those data sets actually almost have too much information. And then the matter is to try to find variables, things like, should I try to average acceleration over little time windows? Should I look at the variance in the acceleration? Should I try to combine the 3 dimensions or analyze them separately? So this whole process of choosing the movement variables that are actually going to tell us about behavior is a whole question in and of itself. Once we've resolved this problem, once we've chosen what variables we can derive from the raw data that tell us something about behavior, then we can essentially treat those variables that we've chosen as response variables for the hidden Markov model. We have to specify the number of underlying states that we think exist in a similar way as we would need to specify the number of mixture components in a mixture model. And then we can estimate all sorts of parameters from this. We would estimate transition probabilities, which are probabilities of moving in the ecological context, the probability of going from one behavioral state to another over one time step. Those are often interesting ecologically because they tell us essentially about the behavioral dynamics of the animal. On top of that, we estimate state-dependent observation distributions. So essentially the parameters of the distribution of the movement variable within each behavioral state.
And how do you approach evaluation of the model?
You mean like model checking?
Like determining its quality. Is it a good model or a bad model? How do you tell the difference?
Yeah, I mean that's a difficult question in some cases. So one possibility is to evaluate what we call pseudo residuals. It's essentially a way to get at model residuals that are a little bit analogous to linear model residuals. So essentially those are supposed to be normally distributed and independent if all model assumptions are satisfied. And so then you could use, kind of usual residual analysis to determine whether any of the modeling assumptions are violated. This is useful in some cases, but it doesn't always tell you exactly what's wrong, and it doesn't always tell you exactly how serious the model violations are. Another possibility that I think is maybe more flexible and more interesting is simulation-based model checking. So once you have estimated all those model parameters from a data set, you're able then to simulate from it. And so simulating from it would mean simulating behavioral state process, and then from that simulating movement variables from it. So those are all things that are easy to simulate from once you have a fitted hidden Markov model. And by reconstructing, one of those artificial simulated movement tracks, you can then compare to the real data and try to figure out what patterns in the real data are captured well by the simulated data and which ones aren't. And any deviations, any discrepancies between the patterns in the real data and the simulated data point to areas where the model missed something. Whether or not that's a serious problem depends on the research question. So that's kind of a whole other question, but it's definitely a good point to start.
I definitely see the appeal of hidden Markov models as a methodology for this particular problem, given some of the parameters you described. But I'm curious, along the way, have you encountered any drawbacks or gotchas with the approach?
Yeah, so hidden Markov models do have some downsides, and it's difficult to describe downsides without thinking about what the alternatives would be. But one of the challenges, definitely, with these models is the necessity to specify the number of behavioral states before the analysis. I think it's also, to some extent, a little bit of an open problem for mixture models very generally. But for hidden Markov models, one of the problems is that if you were to apply, a two-state model and a three-state model and a four-state model to a data set, and then use kind of standard model selection criteria to try to determine which one is kind of a better fit for the given data set, chances are the model selection criteria will almost always select the more complex model. And the reason is that by adding states, we just add a kind of a crazy amount of flexibility. And so it makes it possible to get at much, much more detailed features in the data. And just from the perspective of increasing the model fit, then that's usually appealing. The problem is that once we get to 4, 5, or more hidden states in a model like this, then the interpretation becomes essentially impossible. And the reason is that the statistical states, the clusters essentially that are identified by the hidden Markov model, don't end up corresponding to any actual behavioral states or biological states of interest. They just end up being, very small kind of features in the data, artifacts maybe in the data that are explained away by an additional state. With these models, it's difficult to determine any kind of objective method for finding the optimal number of states, and usually it just requires essentially combining expert knowledge about the system. Biologists often have a pretty good idea for a given species and time resolution of data, how many behavioral states can be identified. And so that's often a kind of a more reliable way of deciding what the model formulation should be, rather than trying to use some algorithmic way, I guess, of choosing it. Another small maybe downside, and that ties in with, I'm sure, a lot of topics on your podcast, is computational cost. And these methods, there's ways to kind of speed them up, but they do end up being fairly computational once you get to very large data sets. This, to some extent, wasn't relevant even probably 10 years ago or something. But now that people are collecting millions and tens of millions and sometimes even more observations using these really high frequency accelerometer trackers, it's almost impossible to fit these models to that many data points on a standard computer. And so I think ideas from machine learning and stuff can really benefit us in terms of trying to speed things up.
Well, I know you're the author of several R packages, a few of them dealing with hidden Markov models. Could you share a few details about the libraries you've created?
The first package that I developed was MoveHMM. So it's a pretty simple R package for essentially the purpose that we've been talking about today, which is really just focused on deriving movement variables from tracking data and then analyzing them with a hidden Markov model. And so this package, MoveHMM, has functions that take you all the way from the GPS data to all the kind of model parameters, transition probabilities, and so on. Another common model output that the package will give you is a prediction for what the state sequence is. This is actually often one of the main things that people are interested in getting, right? Is essentially knowing for each observation, for each time step of observation, was the animal in state 1, which might be foraging, or in state 2, which might be transit. If we're able to identify this, then we're able to identify areas where the animal is more likely to forage, for example, and those kind of answer interesting ecological questions. A few years after we developed MoveHMM, a colleague of mine, Brett McClintock, who works at NOAA in the US, extended it for kind of more general ecological data, and that was partly driven by the need now for a more complex model to also be able to accommodate accelerometer data, maybe three-dimensional movement data and things like that. He developed a package called Momentum, which is also an R package for more complex, more flexible ecological data. And then most recently, I've worked on a third package called HMM-TMB, also an R package that essentially extends the ability to include covariate effects. So the effects of other maybe environmental variables on the behavior state process and on the movement process of the animal in a hidden Markov model framework.
And who's the ideal person to pick up the library and use it? Do you have a sense of who your kind of persona is for the software?
The software is mostly written for ecologists, at least the MoveHMM and Momentum packages. Ecologists who have collected data, and there's hundreds and thousands of studies worldwide that collect data exactly like the data I described, and who are interested in identifying behavioral states or somehow learning about the drivers of animal behaviors from the data that they have. And they don't want to have to implement a statistical method themselves. Well, these packages are written in such a way that it's very easy to pick up, and you just need a few functions for data processing, model fitting, and then plotting and interpretation.
And what sort of technical background do they need to be able to use it? Obviously, they don't have to implement HMMs themselves. You've done that for them, but they should probably have some understanding. What's an appropriate background?
There are a few specific places where understanding the models a little bit is really helpful. And that's partly in deciding on what the model formulation should be. So that's kind of what I was describing before, choosing the number of states. I've sometimes had people come to me and ask, for essentially an automated way to do that, and it's a little bit difficult because you actually need to understand what the choice of the number of state changes in terms of the model formulation, how this choice of the number of states is a trade-off between model complexity and biological interpretation, and that's to some extent a choice that I can't make, that the package can't make, that it has to be done by the analyst, and so they need to be able to think about that. The interpretation requires also the interpretation of the model outputs and the results, in particular things like understanding things about kind of the uncertainty on the model outputs requires also thinking a little bit about the statistical methods that are being used. But I would say that someone who has some experience using linear models, generalized linear models in R would probably not have too much trouble adapting to this, because a lot of the model outputs, the model parameters and so on could be interpreted in some ways quite similarly.
These days, deep learning is really the sort of popular algorithm at the ball. I'm curious if you see a possible application of deep learning in the same way, or is there a reason we would prefer HMMs over a deep learning approach?
Actually, I'll take this opportunity to answer in a little bit more detail a question you asked earlier about kind of supervised learning. But there is a way to use these models in kind of a supervised setting. And so either if you have the patience to go through a part of your data and identify segments that correspond to foraging behavior, periods that correspond to resting behavior, or if you have additional data available, maybe direct observations from the field, or maybe video data that you have kind of concurrently with the tracking data, you might be able to actually build a training data set. So you'd be able to say, I know that during the first day of the study, the animal was resting. I know that during the second day, it was foraging. And then I want the model to somehow use this information to identify for the last 6 months of the data where I don't have labels, essentially, where I don't know what the animal was doing. I want the model to use that kind of training information to learn what the behaviors are and then predict them for the rest of the data. And so in that supervised context, I think deep learning could be applied, and I think has been applied. I'm not on top of all the kind of latest developments in this context. The main reason that I haven't been particularly attracted to those approaches for this particular purpose yet is that I think that they remove maybe the mechanistic description of the animal's behavior as a stochastic process to be modeled with some time dependence that needs to be modeled, and for which we can potentially try to infer environmental drivers and things like that. Those are, I think, the most interesting ecological questions, and I think hidden Markov models have kind of an ideal structure for addressing them. If I can say one more thing about deep learning in this context, I think one area where it would be really useful for there to be more synergy is maybe in data collection, data preparation. I know that there are very kind of new ways, very exciting new ways of collecting data, for example, using drone imagery. So let's imagine that you want to know how dolphins move, and it's really expensive, really complicated to go in the field and try to attach tags, GPS tags on dolphins. People actually do that, and it's kind of amazing that they do, but it's really expensive and difficult. So it might be easier to just go kind of close to the dolphins and fly a drone over the pod and film them for a few hours, and then use the video data to try to infer, trajectories, movement trajectories, and learn about their behavior and so on from this. But it's really difficult. It's a type of data that we're not used to analyzing. You can't directly plug this into a hidden Markov model. And so there's been kind of attempts at using image recognition to try to identify individual animals from images like this, which is really hard when the animal can sometimes leave the video and sometimes return in the video. It's really hard when they go underwater and then come back to the surface. It's really hard when there's very many individuals, and so you need to make sure that you're always tracking the right one. But I'm sure that deep learning, with the amazing kind of improvements in these techniques that have happened over the last few years, will eventually allow us to get these, extremely high resolution, very interesting, very rich data sets for animal behavior and movement.
Well, it would also be very nice if, let's say, an ecologist could look at the model that comes out of the process and verify it in some way. Maybe say, we see the animal is spending so much time in this one state, that's the sleep state, and we have this independent study that says sleeping is about this long, and it matches the time the animal spent there. It's a nice verification, but only with the assumption that the researcher can look at the model and understand the states and things like that. So I guess my question is, to what degree is the hidden Markov model interpretable to most ecologists?
I think the interpretability of the model is one big appeal, at least conceptually, and maybe this is something I'll need to caveat, but I think, on the surface, it's an appealing model formulation, and that's the reason that they've become pretty popular, because ecologists do think about a lot of animals' behavior as being some sort of discrete temporal process where animals sometimes transition from rest to foraging and sometimes from foraging to transit. And the hidden Markov model explicitly, mechanistically kind of describes this. When you end up with transition probabilities and movement parameters within each state, those are all kind of ecologically, biologically interpretable model outputs. Likewise, when we get a predicted kind of state sequence over the study period, that's also something that's very kind of interpretable ecologically, in the sense that ecologists are very interested in knowing when was this particular individual sleeping, when was it active, and so on. All that being said, the main challenge and kind of the main assumption I'm making when I'm describing this as being easy to interpret is that the hidden Markov model states should correspond to behavioral states. And in some cases, we know that that's the case. Usually we need, extra validation data, maybe video data or direct observations, those kind of additional sources of information. Or sometimes, the patterns in the movement, in the tracking data are clear enough that it's almost unambiguous. But in many cases, it requires one step of interpretation that's difficult, where you essentially end up with different distributions for the movement variables. That's the output of the hidden Markov model. And at this point, these are just essentially clusters. These are statistical states that best describe the variability in the data. The model doesn't have any information, any biological input. It's really just a statistical procedure. And then it's the job of the analysts, so in a biologist in our application, to look at those model outputs, look at the movement parameters, maybe the mean speed of movement, and determine, state 1 corresponds to rest behavior, state 2 corresponds to transit behavior, and so on. And if this matching is difficult, if we can't find behavioral states that really match the statistical states that were obtained or estimated by the hidden Markov model, then the outputs are actually quite difficult to interpret. So this is just a big assumption we have to make. And in many cases, it is possible because animals often exhibit very kind of stereotypical behaviors where they have clearly distinct movement patterns. But in some cases, it's difficult to do that.
Well, you'd mentioned earlier that HMMs can be computationally expensive, but I also know computers are getting faster all the time, and you can get a lot of them in the cloud temporarily for an affordable price. Is that a true ceiling that researchers are struggling with?
Yeah, that's a good question. I think you're probably right that if you have the time to look into speeding things up by using clusters and so on, there's probably not very many data sets nowadays that wouldn't be for which hidden Markov models wouldn't be feasible. One challenge is that it's always important to think about what the alternative is. And maybe the alternative would be for an ecologist to go to a simpler model, maybe a linear model or something like that, where they model their movement variables directly with a linear or generalized linear model, for example. And in that case, the model fitting would be almost instantaneous compared to a hidden Markov model, which might take, 5 minutes or up to maybe an hour for a large data set. That difference might seem inconsequential in the grand scheme of, the progress of science, but might be enough to deter some people. So I think it's important to place it, to compare it to other methods that other people could use, and then realize that the reason it's slower than a GLM or something simpler is because it's modeling something more sophisticated, more nuanced about the temporal structure of the data. And so I think there's a good reason, and I would argue that in many cases it's important to take account of that correlation in the data. But some people might disagree and might decide to choose something simpler for the simple trade-off of computational speed.
Well, in terms of what's really cutting edge in the field, where is the front line? Are we looking for better algorithms, better data, or what are you most excited about?
I think there's progress on several fronts. The data are getting increasingly kind of high resolution and high frequency, which means that we are getting more and more detailed information about what animals are doing. This is great because it means that we have less kind of guesswork to do. It means that it's easier to identify specific behavioral states, not just kind of very rough, foraging versus resting, but maybe with high resolution data, we might be able to identify specific predation events or specific scratching events, very, very fine resolution, very small scale behavioral events. The challenge now is to learn how to extract the right variables from these data to then translate those into the behavioral states that we were interested in. So I think there's some really interesting work that's being done right now on this aspect. Another thing is on increasing the flexibility of these models, and that's something that I'm really interested in. Now that we have more data, not just about animals movement, but also about environmental variables, we get really high resolution satellite data for a lot of environmental features. We have a lot of information about how human activity affects animal space use and so on. We are able to include these extra variables into the models to model things or to estimate things like the effect of human activity on the probability that an animal starts foraging, or how does an animal's behavior changes in space or in time. This is something that I've been working on, trying to include nonlinear effects of variables on the dynamics of the animal's behavior. And because the data are getting better and better, we're essentially able to answer better and better, or more and more complex, more and more interesting ecological questions.
Obviously, you're bringing the skills of a statistician and some background in ecology to the table in a nice Venn diagram. Do you think that's an important part for all ecologists going forward? Or perhaps it's always going to be a collaboration going forward?
I think the most amazing thing about my job is the collaboration. I would always recommend that ecologists collaborate with statisticians and vice versa as much as possible. I think that's where the best research comes out of. Earlier, you were asking me about, what background in statistics ecologists would need to have to use some of these models. To some extent, this isn't really a discussion anymore if they're collaborating with a statistician who has more expertise in the field. So that's definitely something that's really good to do. On the other hand, most of my biologist colleagues have, mentioned at one point or another that they wish they had learned more statistics and that their background in statistics was stronger. So I definitely think that even though it's often it seems maybe like the drier part of ecological training, I think that not neglecting that aspect is really important, because realistically, the vast majority of ecologists nowadays are working with huge amounts of data. They're often expected to do a lot of the data preparation, at least themselves. They now more and more need to do data analysis themselves, or at least be able to choose what modeling approach to use, interpret modeling outputs, even in cases where kind of user-friendly software is available. Some statistical background would probably be useful for the vast majority of people going into this field of kind of movement ecology. That being said, I realized that ecologists can't be expected to be statisticians anymore. So then the reverse, and so I would definitely kind of draw a line in how much they are required to know, and beyond that line, collaborations are the solution. Yeah.
And where can listeners go online to learn more about you and your work?
I'm not extremely active on Twitter, but I do have a Twitter page. It's at Théo Michelot. And so you can find me there. I post very kind of sporadically about my publications and so on. If you're interested in my research, you can look me up on Google Scholar and you'll find a list of my publications there. That might be the best place to start. And of course, you're also very welcome to email me. You can find my email online. And if you have any questions about my research.
Sounds good. We'll have links to all the above in the show notes for listeners to follow up. Thank you so much for taking the time to come on and share your work.
Thank you so much, Kyle.